My name is Commissioner Frank Avila, and I'm with the Metropolitan Water Reclamation District of Greater Chicago. And as my guest, I have Bob Johnson. He's a professional engineer and a structural engineer, and he's been practicing all his life. How many years have you been practicing, Bob?
40 years.
40 years Bob been practicing. And today, our show, I'm giving an award, the 2010 award, to Excellent in Education, Educating Our Children in Engineering Award, to Bob Johnson, because he's been educating the kids for over 20 years, and he's been educating his daughter for how long?
29, the oldest one, 29 years.
29 years. So for over 29 years, he's been educating some kid out there. But for the last 20 years, he belongs to a lot of different groups out there, and he's been educating them in the field of engineering, predominantly in structural engineering. And we're very proud. I'm a professional engineer also, but we're very proud to have Bob in our industry to educate the kids. Before the show, Bob was mentioning that engineers are the only profession that have saved most of the lives here in the world. And why is that, Bob?
Because engineers many years ago figured out how to clean water, and it's clean water that eradicated the diseases that were in the water systems. And if you look at the societies that have the best health care, it's the ones that have the cleanest water. And it's the civil environmental engineers that make the water clean, and that saves the most lives in the world.
And that's for drinking water. And since I'm the commissioner at the Metropolitan Water Reclamation District of Greater Chicago, what we do is that when I go give talks to the school with the first graders and the eighth graders, I say we clean poop and urine. They understand that. They understand poop and urine, and that's what we do. So as Bob is right, that we purify the water for drinking purposes, and we clean the human waste to recycle back into the environment.
In fact, when I was talking to kids, one of my first lectures, I mentioned that where does the water go when it goes down the toilet bowl?
Yeah.
And the kids couldn't think of it, and I says, well, you drink it again. And I had the kids literally in hysterics saying, you mean we drink that water that goes down the toilet bowl? And I said, yes, you eventually do, because it's recycled.
Because the water cycle.
It's water cycle. It's made clean again and put into the water system, into the rivers, and then it's evaporated up into the air, and then comes back into the lake. So that water that's made dirty is made clean by engineers, and the kids now started to think about the importance of clean water.
And it's the same water that people drank 2,000 years ago.
The dinosaurs drank the water.
Right. Same water. Same water, because you don't produce water. You don't make water. It's what's here that we have on the planet. And Bob, so this is our 2010 Excellent in Educating Our Children in Engineering Award, and I'm very happy and proud to give this to you, Bob.
Well, thank you, Frank. I really appreciate this for what you're doing for me, and I hope my fellow engineers and the kids appreciate the importance of engineering, and this goes to recognize the work I've done, and I can't say enough how much I appreciate the, thank you for the award.
And so what we're going to do on this show, and then we'll put the award down here, okay? Let me. What we're going to show, what Bob is going to show today, what he has been doing for the last over 20 years on how he's going out to the different, and he belongs to a lot of different groups. He's a structural engineer, and he probably started out with the Structural Association.
Yes.
And then from there, he probably went on to Future Cities. To what are some of the other groups you work with?
Well, I've been participating and networking with the first competition. That's the robotics competition.
Robotics?
There's now the ACE Mentor program here in the city. There's other programs. There's dozens of programs reaching out to kids to teach them STEM activities. STEM is the acronym for Science, Technology, Engineering, and Math. And there's literally dozens of programs to interest kids in science, technology, engineering, and math. There's the Math Counts program. There's now the Construction Challenge program. You just mentioned Future City. There's a Lego robotics competition for kids. And it's all out there to interest kids in the importance of science, technology, engineering, and math.
And you know what? Not only does he educate the kids in what he's doing, he's also educating the teachers and the parents.
You know, when the parents come to the conferences or the seminars or the lectures, the open houses that we have, the parents come away with a better appreciation of the world around them and learn how the buildings in the city stand up, how the bridges stand up, and the importance of engineering in our society.
Yes, so through over the 20 years, Bob have introduced engineering and taught engineering to maybe thousands of kids over the last past 20 years. Now, Bob has here his display here, and what Bob did, and if anyone see that the Sears Tower is not there out on Jackson Street because it's here. Bob had it carried here. He brought it here in the wheelbarrow, I think, Bob. And also, he has the John Hancock Building here, and he has some bridges that he took from the city of Chicago, but we're going to replace it after this show, and I'll help Bob carry the Sears Tower and the Hancock and the bridges back to where they're at in the city of Chicago.
Oh, by the way, it's not Sears Tower anymore.
Oh, no, you're right.
It's Willis Tower.
Yeah. So Bob, explain to us what when you go in and on these conferences with the students, what do you show and teach them?
Well, when I first got started in this actually it was back in 1989, my daughter was in first grade, and I was called in for a conference with the kids to explain to them about what engineers do. Now, how do you teach a first grader what engineering is all about? Yeah. I mean, the public even has a hard time explaining what an engineer does. I tell my friends that I'm an engineer and I design buildings. And they say, "Oh, you're an architect." I says, "No, I'm an engineer. I designed the buildings so they stand up." So even the public doesn't have an appreciation and understanding of what engineering is all about. So then I asked myself, how do I teach first graders? Well, it's surprising. Think about the first graders. They are engineers. They don't know it, but they started off with building blocks when they were kids. Yes. All of us were engineers when we were babies. You became 3, 4 years old, and you started with your building blocks, playing with blocks, except I haven't grown out of it. I got my building blocks are concrete, steel, masonry, wood, but getting back to the first graders, again, how do you teach a first grader what engineers do? So I came up with some simple demonstrations. And one of the simplest ones that I deal with kids on is I give them a slab bridge.
A slab bridge?
And this is just a piece of paper, and I put it on my supports here, and I'd say, I want you to hold up that slab bridge, and I want you to hold up this pen with it.
Okay.
And we go like that, and we find out the slab bridge fails.
It failed.
So then I keep on asking the kids, there's something you can do with this piece of paper to get to hold up this pen. And I have the kids kind of think about what you can do with the piece of paper. And eventually the kids will start folding it.
Oh, excellent.
And I go, you've got the solution, but it's a little trickier. Is ideally you want what's called a folded plate, an accordion type fold. So we have this folded plate. We can put it on our supports here, and we can put our pen on here, and it'll hold it up.
It doesn't. But, here, let's put the slab back on and show them how it fails. So here, he puts this pen here, and it fails. And now here he has an accordion, but this really doesn't play music.
No, that's the accordion type folder, and it's called a folded plate. But that's too easy. We're just holding up a pen. So let's take a bigger, heavier weight and put that on here. And let's see if we can do it today. If I'm really lucky, sometimes, depending on how good I fold it, I can get it to hold up another piece of weight.
Oh, excellent.
And now we get the kids thinking about how shapes are important to holding up structures.
Yes.
But then the kids might ask, what's this got to do with engineering? So I bring out this piece of deck, and here it is in real life. This is a piece of metal deck that's used to hold up office buildings, hospitals. We place concrete on top of this. This deck is placed on beams, and that's what's holding up our office buildings, our hospitals, even your school.
Now, how thick is the deck on high rises?
What they're doing now is the deck, is 3 inches deep.
3 inches deep?
And it'll span between the beams 15 feet.
Okay, and also inside the concrete, they put some
mesh.
Mesh?
This is the reinforcement for, the deck is the reinforcement for the concrete in this type of structure.
Okay.
So that's one little example of how we can explain to kids on how structures stand up. But there's all other kinds of demonstrations I show children. Simple square or a diamond. You can see that it's not very stable.
Right.
Okay? But triangles are important. And I tell the kids, when you get to high school, you're going to have a whole course on the study of triangles. And that's how important they are to engineers. And you can see you cannot get it to move.
Right, on different ratios.
On different ratios. Now, we can put a whole series of triangles together.
Yes, look.
And now we have our truss bridge. Now, Frank, push down on here.
Okay, right here.
Okay, and you can see the bridge will stand up. That's pretty strong.
That's pretty strong, yeah.
Now, this is an interesting demonstration to show how bridges function. I'm going to flip this over, and I want you to push down on it and see what happens.
Okay. Yes.
You can see the triangles come apart. And this simple demonstration shows you hold that end, and I'll hold this end. When you push down here, this is pushing together, and down here it's pulling apart. And the triangles here are paper clipped together on the bottom, so that prevents the triangles from pulling apart. If we flip it over, we go like that. There's no paper clips down here holding it together, so the bridge fails.
And the older type bridges that they used to build in 19
Here's this is actually from my childhood days. This is from my model train set that I had when I was a child. And here we have an example of a railroad truss bridge.
Right. And also even your bridge going over a stream where cars went over. That's how they used to make the bridges. Yes.
And another thing, I go talk about the bridges, and here's something. It's a sad chapter in our engineering history, but this just shows to the kids and the public. Some of the people may have recalled, and I think it was 2007, a bridge up in Minnesota collapsed.
Yes.
And what they did trace the failure to was this thing, plate here is called the Gusset Plate. It's used to collect and connect the members. And what happened was this member and this plate wasn't thick enough to transfer the load from this diagonal into the other members, so this plate failed and the bridge came down.
And that bridge went over the Mississippi River.
Right, in Minnesota.
Yes.
But this is just to show how the pieces get connected up, and the reason for the tragic Minnesota bridge failure. I have other demonstrations that I give to the kids and to show how Chicago skyscrapers stand up. Here we have a simple frame structure. And as you know, we have winds in Chicago, and we can get this thing to blow. And it'll wobble back and forth. All buildings will do this.
Yes.
But we have to make it so that buildings don't move as much. So there's things we can do to make the building stronger. One is to put in these panels called shear walls. And we put the panels in here. And now this structure will not move. You can blow on it, Frank, and I can wobble it back and forth. And
now, are your shear walls, are they mainly in the core area of the building by the elevators?
Yes.
They put and that's where predominantly you might find the shear walls?
This one I like to show the kids and the public. What we see in a skyscraper is the pretty outside.
Yes.
The architects call this a curtain wall. This is nothing more than a curtain that holds up the structure. And we open up the structure to expose, take off the curtain wall to expose the structure. And there we have the central core, which is concrete, and we have our floors and our outside columns.
And this is the shear wall.
The shear wall's on the inside.
And also the elevators are inside.
And your stairwells.
And also on most of the high-rises, Bob, maybe the first or second or third floor are not typical.
Right.
But after
they're higher up.
They're higher up. Yeah. Maybe after the above the mezzanine or something, they're predominantly typical.
Now, what else we can do to strengthen buildings is put in bracing. If in a steel building, they don't have concrete walls. They'd have steel bracing. And you can see here, this one's not going to move. And believe it or not, there's actually a building in Chicago that looks like this one here that's about, on the near north side. But maybe you'll recognize the shape and the triangles, again, that strengthen it up. Here we have the triangular shape. Now we take this to the extreme.
Now, there's also, isn't the Daily Center structural steel?
The Daily Center is structural steel, but let me just show you this one here before you, is the Hancock Building.
Yes.
And if you look on it real close, we're going to blow the wind on it here this way, push on it. And if you look real close, you'll see these strings tighten up, stretch, and the strings the other way compress and shrink. So here we go this way, and you'll see, let me push on it, you'll see that string shorten up and that one's tighten up. And when you go this way, it's just the opposite. And this prevents the Hancock Building from moving in a windstorm.
Now, what's the maximum movement on top? If there's
the rule of thumb engineers like to use is about the height divided by 500.
500?
So let's say the Hancock Building is a little over 1,000 feet.
1,000 feet.
Divided by 500 means the Hancock moves about 2 feet either way.
Sears, on
the top. Sears Tower is about 1,500. Actually, it's 1,450, but let's use 1,500 divided by 500 is about 3 feet.
But you're not feeling it.
You're not feeling. This is the hard thing to explain to the public about building movements.
Yes.
And I'll give you a little bit, take you back to your physics days.
Yeah.
Think about when you're in a plane. You're going 600 miles an hour.
Yes.
You don't feel it.
No.
Okay? The minute the pilot slows up the plane or on the runway, what you feel is the acceleration, the change in movement, the braking action. So it's not the speed, and it's not necessarily the movement. It's the change in movement, which is called acceleration.
Yes.
So when the building moves back and forth like this, it's changing its direction, and that's what you feel. And so long as the building is moving slowly enough, you're not going to feel it. But if it was to go like that, then you'd feel the movement. So what the engineers have to do is make sure this movement is slow enough that you don't feel it. Another building which you just mentioned too that we brought over here today is the Sears Tower, or I should say Willis Tower.
Willis Tower. So we'll bring this back after the show.
I made this crude cardboard model again to show the kids and the public, the parents, how Sears Tower is built. And Sears Tower is nothing more than 9 buildings tied together. And here we have the 9 boxes. There's 9 buildings that are tied together. And the engineers called this a bundled tube.
And now, was it, he passed away, but it was
Fazler Khan was a very famous structural engineer here in Chicago. He designed the Hancock Building. He also designed the Sears Tower and the Hancock Building.
And and on this building here, since it was so not much movement on the outside to build this building, they had to bring the truck up with the steel that was loaded on at different times. And they had to coordinate all of that to build the Sears Tower.
The other thing, I like to point out to the kids with regards to the engineering of Sears Tower and other buildings, and people just don't think about it, and we'll go back to the issue of water.
Yes.
How do you get water up the top of Sears Tower and push it up? Because the simple experiment is you take your water hose and shoot it up into the air, and it'll only go up maybe 2 stories.
Yes.
So engineers have to pump the water up. But that gets to be very expensive to pump the water up. So if you ever to get high enough and look at Sears Tower, you'll see on the setbacks huge water tanks. And a lot of your super tall buildings, they like to put the water tanks high up, pump the water up there, and then have those big water tanks on the top of the building. So then the water then flows down.
Gravity flow.
Gravity flow, right. Gravity flow down. Now we have other types of experiments I give the kids and tests. Let's do another simple one. Let me get my board out here and bring this one out. Here we have, again, another bridge, and my supports are here. What I do with my supports, I give the kids these supports,
Okay.
and I put it on here, and then I put my weights on it, and it's not too strong.
No, it's not. It's
Okay. Let me get this one here that's a little bit, this one's pretty strong.
Okay.
So let's put this one on here. And now, as you can see, it's really not strong.
Oh, yes, yes.
But there's something you can do with these pieces of cardboard to make it stronger. And we'll do it one more time. See, not
Okay.
very strong. So what can we do, Frank, to make
maybe
this?
you put stiffeners or
No,
No?
there's something really simple you can do with this. We're going to make an arch.
Okay.
So we put the arch. This is your deck. Now we have an arch bridge. And we can put our weights on here. And there we have a simple arch bridge.
Now, where are some art bridges that we have? We have
One of the not famous, but soon to be really famous bridge, and it just opened up,
Yeah.
is right in front of the Hoover Dam.
Hoover Dam.
They've just opened up a brand new arch bridge in front of the Hoover Dam.
And what's the span on that?
I don't know if it's about 900 feet.
900 feet?
Yeah, I think it's about 900.
Oh.
I'm not sure, but it's
Yeah.
pretty impressive. You can go on the internet and just look on Hoover Dam bypass, and you'll see the bridge. It's really a beautiful bridge. Other things we do with regards to arches is explain to the children how arches work. And we go over here. Let me get my little demonstration here. It's important to show that arches aren't necessarily too strong.
Now, they have used arches.
The Romans were the ones that invented it or started really using it. But here we have an arch, and notice what happens with the arch if we let it go. It wants to flatten out.
Yes.
So we have to do this. We have to put in anchorages at the end. These are called dead men. And now the arch will stand up, and we can load it up. So this, again, to show the principles of an arch. But there's another thing we can do with arches. And we have bridges like this, is we can tie the arches with a tie across here.
Tension?
A tension tie.
Yes.
And we'll go back to my bridge support here and take this one off.
Okay.
And we can put our arch bridge with a tie across here, put it on our supports, and now we can put our weights on top of this.
Oh, excellent.
And there we go.
And they have, some of the high rises too have tension too.
Tie, right.
I think my last project I worked on was the jailhouse job on Van Buren and Dearborn.
There's other ways we can also tie bridges, and I like to show this little model I created. Is we can have this bridge here, and we can load it up, and you can see it's gonna deflect. And you notice here what happens to the strings.
Yes.
They're not very strong because they're in compression and pushing together. But notice the difference in behavior if I turn this over. Now we can load it up, and I can keep on adding weights on here, and this will hold up the bridge. And this is sometimes called a king post type truss. So this shows again to the children, students, even the parents, how structures function. Let's go back. You were also mentioning arches and buildings, other types of buildings. Back around, I think it was probably around the 1200s, they were starting to build bigger and bigger churches.
Yes.
Okay? And here we have just a simple representation of a church.
And that started in the 1200s?
About the 1200s, they started building the bigger and bigger churches.
Okay.
Eventually it evolved into what we call now the Gothic Cathedrals. And you'll see here that these walls aren't too strong.
Yes.
They learned when they were building these huge churches that the walls were collapsing on them. So what they had to do, they discovered what we had to do was build in what we call now buttressed walls. And if you take a look at a lot of the churches in the Chicago area, you'll see these walls sticking out the sides of the churches or even in the insides of the churches. And now when we push on it, it's not going to move. And that's the classic, the 1200s or 1400s, the Gothic cathedrals.
And just think of that, in the 1200s, they were designing and imagination and came up with different types of design. And you know, when they first started building, they didn't have
computers.
They didn't have, or schools to learn. They just learned on their own.
Right.
What worked and what
didn't work.
Yes. And then someone came out and said, well, you got to use a 3-4-5 or any type of a ratio to make that building sturdy.
Unfortunately, with regards to a lot of building history, you learn from your mistakes as you get bigger and bigger. And I guess the kids and even the parents have probably seen the famous video of the Tacoma Narrows Bridge.
Oh yes.
Gallup and Gertie in 1940s,
right,
where they built a bigger and lighter suspension bridge in Washington, and they built it so light and flexible that the wind got a hold of it and destroyed the bridge.
Yeah, the wave, and I don't know how long it took, but I saw that film, and people were actually walking on the bridge. Yeah. There and
it was well, for the first 6 months. It only was in operation 6 months.
Right.
And they were having a hard time walking across it, and cars were having a hard time going across it. And finally, during a really bad gale, it wound up collapsing. Nobody was killed, but the story I had heard, they lost one dog that was trapped in a car.
And Bob, you were born and raised there in the Chicagoland area?
Yes, I grew up on the far northwest side of the city.
Okay. Which area was that, Bob?
Edison, Norwood Park area.
And then you probably went to Taft High School.
Yes, I went to Taft High School.
High School, yes.
You know the trivia I like to tell. I like to tease my friends or point out the history of Taft.
Yes.
Taft is the original Grease School.
Yeah, Grease School, yes. Because
the class of 1960 is known as the Grease class. Yes. Actually, I came in 61. So
61?
But I knew well of the Greasers.
I see. So Bob, he's a good dancer and he's a good singer.
Yeah.
He knows all those songs.
Actually, when I was going there, my term for me would have been called a collegiate.
Okay.
Because those were the boys and girls that were on the track to go to college.
I see.
We were known as collegiates.
Well, I think Bob, if he would have gone to school earlier, he might not have been a structural engineer to help our kids because he would have been in show business. But I'm glad that he came in 1961, and we're very fortunate to have people like Bob Johnson to come and teach our kids and introduce them to the world of engineering. And Bob, we went to Taft High School. Then after that, you went to Illinois Institute of Technology, IIT, right down the street.
Yep.
And
33rd and State.
And we have very good schools in Chicago to send our kids. And if anyone needs Bob's service to come and teach your school, what's your phone number, Bob, to go, because you're retired and you do this on non-profit?
Well, what I've been doing lately is doing it at big conferences like the big display.